So glad that you were able to make it. Hey, I
I was
want to talk
watching.
about intersections. I want to talk about intersections with you because I noticed that you were having kind of an issue with intersections. But what would you like to start with? We'll sure get to that. It might not be the first thing on your mind, though. What's the first thing on your mind?
We can start with the intersections, and I still want to go over the special homework, the last one.
Oh yeah, on
Um,
on sets.
yes,
And
because
you
that I
are
think
Tuesday, Thursday, right?
yes, because I think that one was the one that really confused me, and I was looking at the notes and
I'm going to share something with you. I'm
all
going to
right.
open up my files from test three and let's look at test three. Can you see that?
Yes.
This is test three, form B, okay? And that is the form that Monday, Wednesday took because things were, a little bit off one day. I want to show you, it's a very similar test. The real difference was this. This was the set. Trying to get this out of the way. I'm trying to make this go somewhere else. Anyway, do you see it?
Yes. This is what you were talking about that wasn't on
Yeah,
our test,
it
but will
wasn't
be on
on
the
your
final.
test, right? So it was a subset inclusion proof, right? Let's just
Mhm.
walk through it together and let's see if you do a little better when it's sort of laid out for you. If we're trying to prove that this set, A complement intersect the quantity B union C, is a subset of, right? That's what that means, subset of this set, right?
Mhm.
Do you know what the procedure is? Like, where do we take an X and where do we wish to show the X would live? For example, I started the proof and I just said, hey, let's let A, B, and C be subsets of some universe. Okay. And then assume X is an element of blank. Okay. Do you know
What
what you should assume X is an element of?
would it be a com union B
This is an intersection.
intersection B union C?
Yeah, it's this set. So we take an X in there. Where do we wish to show the X lives?
A complement intersect B union A complement intersect C.
Nicely done. So
Okay.
we wish to show X's in there. So that's the first two. You got them just fine. So remember, X is in A complement intersect B union C. So by our hypothesis, we know, wonder if I could even write, wonder if I could even draw, type. Maybe I should try to draw. Okay, so let me see if I can draw. Assume X is an element of A complement intersect. I've never done this before. I'm just using my mouse. B union C. Can you see it?
Yes.
I'm just doing that so we can see it. And then we wish to show X is an element of A complement intersect B B. It's hard with the mouse, right?
Yeah.
Union A complement intersect C. All right. So at least that way we can see what we've got. So by our hypothesis, we know X is an element of A complement and X is an element of what?
B union C
By definition of,
intersect.
uh-huh, right? We just broke down uh, this intersection. Now, so X is an element of A complement and X is an element of B union C. We're just breaking down what it means to have X in that set here. Since X is an element of B union C, we know X is an element of B or what?
B or um, C.
That's right.
I was writing it down.
By definition of,
Union.
that's right. So we know that or leads to cases, right?
Yes.
I'm looking for the eraser. Oh well. So suppose X, so, right? So we know X is in B or X is in C, right? So suppose X is in B. We also know what? You read it.
We also know X exists in C complement by our hypothesis. So X exists in in B. No, in C. Oh no. B union C. No, B. Yes, it's B. Wait. B. B.
Look at what we wish.
B union C.
Nope. Look at what we've got. We've got that X, we're supposing X is in B. Okay.
Mm-hmm.
We also know X is in A complement. So we know that X is in B and X is in A complement. So X is in something by definition of intersection. Well, look at what we just stated. We said X is in B and X is in A complement. So where is X by definition of intersection? It's in both A complement and in B, right?
Yeah.
So we could write B intersect A complement, or we could write A complement intersect B. Do you agree?
Yes.
You see what, look at where we're trying to get to. See, we want to show X is in A complement intersect B, union A complement intersect C. Well, B intersect A complement is the same set as A complement intersect B, right? Because intersection is symmetric. So I just tried to lead you through it. So since X is an element of A complement intersect B, I'm just switching those around. It doesn't matter what order they're in. The statement, why don't you read this?
The statement X exists in A complement intersects B or X exists in A complement intersect C is true.
Do you agree with that? That since we know X is in A complement intersect B, then the statement that X is in A complement intersect B or X is in A complement intersect C is a true statement?
Yes, because X has
So,
to be in one of them for it
yeah,
to be
and we
true,
got
at
it.
least.
Yeah. So X is an element of A complement intersect B union A complement intersect C by the definition of what? Look what we're doing. We're taking an or statement. All right, this is just a statement. This is a statement. And we're changing it into a set expression involving,
The union.
yeah, because we're switching or into the union symbol. Does that make sense that we can do that?
Hmm.
All right, remember we had two cases based on the fact that X was in B union C, right? We had
Hmm.
X is in B or X is in C. We just dealt with the case when X is in B. All right. What's the other case?
Suppose X is in C,
Wow.
and then we still know that X exists in A complement by the hypothesis.
Good.
So X exists in A complement intersect C by definition of intersection.
Exactly. Keep
And
going.
since exists in A complement union intersect C, the statement X exists in A complement intersect B or X exists in A complement intersect C is true. So X exists in this, would that be the whole statement?
Like the whole,
The A complement intersect B union A complement intersect C.
exactly. By definition of union, right?
Mhm.
So finally, ah, so we've shown that X is in that set
Mhm.
in each case. We did it in two cases, right?
Yes.
So then we have shown, let's go back to the beginning, that X in this set, right, implied that X was in this set, right?
Mhm.
We started with an X and A complement. So, I mean, I'm just not going to write it now because my writing is crap with the cursor, but you get what I'm saying, right?
Yeah.
We proved that X element of the A complement intersect the quantity B union C did imply that X was an element of this big set. As you said, the whole thing. So we have, can you read this last statement?
Thus, A complement intersect B union C is a subset of A complement intersect B union A complement intersect C by definition of subset.
Exactly. That was the that was the question on set. That was our set proof question. I sort of, baby job with that, babied them with that. But we'll certainly look. I just wanted to give you an idea of
Okay.
what's gonna, what could. Hi, Rebecca.
Hi.
All right, so shall we look at special homework number 11?
Yes.
Okay. And Rebecca, hi. Did you have any particular things that you wanted to look at?
Um, I think the intersections which we were doing before, and then the the what's it called again? The I'll get back to it. I forgot.
All right. So shall we look, if we don't understand intersections, though, maybe we better first look at intersections, okay? That operator, given sets A and B, you know, and a universe U, A intersect B, supposed to remind us of the AND operator. It's A, and that symbol should kind of remind of the AND operator symbol. A intersect B is defined as, you can help me with this, A intersect B is the set of elements little x in the universe such that, so what is the definition, Sydney, of A intersect B? Could you tell me with your own words what would be an A intersect? What elements would be in A intersect B?
Um, I think this was the class I showed up late to, so I
Well, you sure need to know these definitions, and they've been in the class notes. We also did this back in section 1.2. That was the second class of the semester. It's X that's in A and in B. So X is in A intersect B if X is one of the elements of the universe and X is in both A and in B. So if we drew a picture just to get a visual idea, here's our universe. Here's sets A and B. We don't know, how many elements they might have in common, but the idea is they may have some elements in common. And that area that's called the cat's eye is the A intersect B area. The elements that are in both A and B, okay? So let's just look at a couple of simple examples, shall we? Let's look at a finite example and then an infinite example. Let's let A be the set that contains 1, 2, 3, 4, and 5. And let's let B be the set that contains 1, 3, 5, 7, and 9. And let's let C be the set that contains 6, 7, and 8. Okay? Let's find A intersect B. Let's find B intersect C. And then let's find A intersect C. Okay? You with me?
yes.
All right. Two black pens. Where's my blue? There's my blue pen. Okay. So A intersect B. Let's find it. It's a set. Tell me what elements would be in A intersect B.
3 and 5.
Yep, because these are the elements that A and B share. Good. What's B intersect C?
7.
Yeah, that's it. It's a little singleton set, 7. What about A intersect C?
It's empty.
That's right. Good. All right. And now let's look at an infinite example, shall we? Let's let A1 be the set, square bracket 1 to 2 square bracket. So these are, infinite intersections. Okay. And let's let B be the set. Oh, sorry. Let A2 be the set that goes from 2 to 3. And A3 be the set that goes from 3 to 4. Find A1 intersect A2. Find A1 intersect A3. To draw pictures on the real number line if it helps. Let's find A2 intersect A3. And then let's find the indexed intersection from K equals 1 to 3 of the A sub K, where A sub K goes from K to K plus 1, inclusive. It's closed with the square brackets. Okay. All right. So what is A1 intersect A2?
Square bracket 2.
Well, yeah. But square bracket, has 2 numbers in it. You could write it as going from 2 to 2. I think that even in WebAssign, it's not Susanna Epps that's doing that. The publisher hired people to try to implement the homework, okay? I don't think she would go for this very well, but it's just a singleton set with just 2 because they overlap right there at the endpoint, don't they?
Mm-hmm.
What
So if
about
it's coordinates, so
coordinates? These are not
or
coordinates.
not coordinates, but when it's
Intervals.
intervals, why did you write it from to the 2?
Why did I write that as
Yeah.
the intersection? Let's draw a picture. Let's draw a picture of these sets, shall we? Here's 1. This is a real number line. Here's 3 halves, right? There's a bunch of numbers in here, an infinite number of numbers in there. Here's 2. Here's 3. Here's 2.5, 5 halves. Bunch of numbers in there. Now here's 4. Here's 3.5. Oh, 7 halves. But there's a whole bunch of numbers in there too, right? All right. So A1. Do you understand that A1 starts at 1 and includes 1 and goes all the way to 2 and includes 2 and it includes all these infinitely many real numbers in between. You understand that, right?
Yeah.
Well, A2 starts at 2, so A1 and A2 share 2. They both have They both have the real number 2 in them. A2 goes to 3, and A2's got all these real numbers in here, plus the endpoints. So why did I say it's the set that starts at 2 and ends at 2? Because this number, x equals 2, is the only real number that A1 and A2 share. You can actually, it's okay to have interval notation where these two numbers are the same, okay? It just means that this is just that singleton set with just that number in it, okay? That's why.
Okay.
You didn't see that when you did some of your website?
I did, but I was still just like a little
Yeah,
confused.
yeah. I left you all to figure that out on your own or to read it. You know, there's that little option where it says read it. Yeah, have you ever clicked the read it option?
Maybe once or twice.
You should probably do it more often than that.
Yeah.
Okay. Didn't mean to put you on the spot.
Okay.
I feel bad saying it.
It's the
But
truth.
anyway, that's what it is. It's just this, or you could add. It's just, but you're finding out now. Hey, you're finding out now, right?
Mm.
So let's go ahead and find out what A1 intersect A3 is. So we're taking the set from 1 to 2 inclusive, and we're intersecting it with the set from 3 to 4 inclusive. This set that's done in, I think that's a black pen, and this is done in green. So what's the intersection of those two sets?
Would it be empty?
It sure is. There is no X that's over here and at the same time over there, right? What about A2 intersect A3? A2 is from 2
Would
to,
the interval also be 3 to 3? And
uh-huh.
then the set would just be the element 3?
Yeah, very nice. So you get it. Now let's look at this intersection from K equals 1 to 3. All right. So it helps to actually understand what that intersection really means, right? You agree that this notation means A1 intersected with A2, keep going, intersected with up to A3. You understand that it means we're intersecting all three of these, right?
Yes.
So we're asking what elements, this will be X in the reals such that X is in A1 and X has to also be in A2 and to be in this triple intersection, X has to be in A3. So we're looking for X's that are in A1 and in A2 and in A3. Keep in mind, you already looked to try to find X's that are in A1 and A3. There weren't any in there. Do you think intersecting with more sets is going to make anything better happen as far as finding elements that are in that intersection?
No,
That's
because
right.
it's still going to be empty.
Yeah, it is. There's no X's here and here and here. The only two X's that are shared are not even shared between all three, right?
Mm.
So these aren't pairwise disjoint, right? So that's something to understand. Sort of where Rebbesign fell down. Notice the collection that has A1 was had a good bone, Rocky. My dog just had a soup bone. He is so thrilled. The collection that has all three of those sets in it is not, now he's thirsty, a pairwise disjoint collection. of sets because, you were able to find out for yourself that we take some of them, sometimes there's something in their intersection, right? Because, A1 intersect A2 had 2 in it, so it was not empty. And like you said, A2 intersect A3, you could write that here as the reason, had 3 in it, and that's not empty, right?
Mhm.
But the intersection of all of them,
Is empty.
yes, because there's no X that's in all 3 of them. Okay. All right. So this sort of idea of hey, we got to watch out, what's going on with intersections is worth looking at. I think I gave you, I don't know if it was number 7 double prime. I gave you a do later. And I think the do later was a problem that was actually given on the test for the Monday, Friday people. It was where B sub k was negative 1 over k to 1 over k closed on both ends. Wasn't that number 7 double prime?
Yes.
That was a do later from 12 by 25 pop up office hour. And there were a couple things, you were supposed to find the union from k equals 1 to 4 of the B sub k, right? And then you were going to find the intersection from k equals 1 to 4 of the B sub k. I think you did those right. But then when we looked at the infinite union,
That's where I messed up a little bit.
yeah, we're going to look at a picture and hopefully help you get that sorted. And the intersection is really interesting too, okay? And then finally the question is, the set B1, B2, B3, B4, a partition. It was square bracket, wasn't it?
The
It was square brackets on both sides, wasn't it?
square bracket from 0 to 4.
Oh, did I ask if it's a partition of square bracket from 0 to 4?
There
I,
was the
I
first one
no,
was
I think I meant to say, is it a partition of square bracket negative 1 to 1?
because I had that one as soft
Oh, is this
brackets.
one solved? Really?
No, that was square, but the first 7
The
prime
first was
was
different. It went from like minus K, or it went from K minus 1 to K or something. Yeah, or yeah, it went from
I
K
think I
minus 1 to
just
K. Go back and look. But anyway, let's look at this one because this is the one you sent me.
I think I just probably put the wrong ones together. I think that's probably what happened. But we could
Okay.
go over it.
Well, hey, that's good news. If that is what happened, I'm kind of glad to hear that, right? So that
Yeah.
means we should be able to get, you got this part right. Like, let's just take a look. What is B1?
B1 is -1 to 1.
Great. What's B2?
-1/2 to 1/2.
Yeah. What's B3?
-1/3 to 1/3.
Right. And of course, B4.
-1/4 to 1/4.
And you did draw a number line. When I looked at your work this morning, I appreciated that you took the trouble to try to scan that, and get that to me. You definitely, that was a good effort.
I don't know what was going on. The file just wouldn't open, and I
Yeah,
tried
well,
for
sometimes you have to
an hour.
close the app and
Yeah.
you know what I do with those? I'll show you if we have, if we feel like doing it tonight. I don't know what kind of phone do you have?
I have an iPhone.
I know people that love them, love them. It's a different operating system. All right, so the negative one half is halfway between, right? The negative one
Mm.
and the zero, and the one half is exactly halfway between the zero and the one, and then the one third and negative one third. Well, it's supposed to be one third of the way, right? So if that's third, then this would be like one third, and then one fourth is like here. And then one fifth would even be closer. I mean, they get closer and closer to each other. Kind of interesting the way these fractions behave. There's nothing in between. There's nothing from minus one half to negative one, but the space between here and here is the same as the space between there and there. So all of them are, no, as you go to infinity, these sets they're nested, right? You understood that, right?
Yes.
So here's the smallest one, B4. Oh, oh, was it supposed to be square soft brackets? Doesn't matter. That actually does matter. We have to have square brackets, otherwise it's not going to make any sense at the end, I think. It could go either way. But anyway, here's B4. It goes from negative one fourth to one fourth, right? But B1, is this big one that's all the way across, right? From negative one to one. And
Mm.
then the other two are sort of in between. But we're seeing enough to see what's going on. So what's a union? B1, union, something that's contained in B1, union, something that's contained in that, union, something that's contained in that, right? Because it isn't B4 a subset of B3, and isn't that a subset of B2, and isn't that a subset of B1?
Yes, because they're all nested.
Yeah, did I do this the wrong way in the notes on Friday? Did I screw that up?
Mm-mm.
I didn't say the
No,
wrong thing there. Okay.
no, because we
Okay.
were talking about
A different set. We were
yeah, the
talking
one on
about
the test.
yeah, right, where they got bigger and bigger and bigger.
Mm.
We were looking at this one, weren't we? But
Yeah.
now these go the other way. They're nested. They don't get bigger and bigger and bigger. They get smaller and smaller and smaller. So what is the union?
-1 to 1.
Yeah, because all the other three are contained in B1, which is from negative one to one. So you've already got all of the elements you're going to get right there at the very start, right? Right. Good. Now, what about the intersection?
Um,
Rebecca's is helping you too.
Yeah.
All right, so if we're going to intersect, let's just think we're going to take uh, it's got to be elements that are in the set from negative one to one, and also they have to be in the set between negative one half to one half, and these x's in this intersection have to be in this next set, and they have to be in the set before from negative one fourth to one fourth. So they have to be in B4 and they have to be in B3
so would it be
and
from -1/4 to 1/4?
exactly right because those are the elements that are in all of them. It's just these little middle elements that are in there. So it is B4, yeah. Good. Now, if we keep taking the union out and keep going forever, so you're saying, okay, we're going to take -1 to 1, and we're going to, union it with -1/2 to 1/2. And then we're going to union it with all these, but just keep on going, union -1/100 to 1/100, union, keep on going to -1/1,000,000 to one. I mean, see what I mean? Like, so even if this union goes on forever, what is the union? This is union now, not intersection. We're talking about the or. Elements that are in B1, or in B2, or in B3, or in, B4, or in B5, or in B6, or in B1.
So, would it be from -1 to 1?
It is, because that's as big as it gets. All the other elements and all these other sets are already in B1 from -1 to 1. Does that make sense?
Yes.
Great. So taking, making this union go bigger and bigger and bigger doesn't give us anything new. Whereas the union, if we keep going forever with this set, it just, union -5 to 5, union -6 to 6, union keep on, it just gets more and more and more. It just gets to be a bigger and bigger and bigger set, right? Because more and more good stuff goes into that set.
And that would be from -infinity to infinity. Keeps getting
Exactly.
bigger and bigger. Okay, I'm
Yeah.
getting it.
This one's getting smaller and smaller.
Okay, I'm getting it.
You getting it?
Yes.
Oh, that's awesome. And now if we play the intersection game, okay, so here's the mind bender. We're starting with this set from -1 to 1, but the elements that are in the intersection have to be in this set and also have to live between -1/2 and 1/2. So now so suddenly, our world is half as big, right?
Mhm.
And the X's that are in this big intersection also have to be in B3, so they have to be restricted to being between -1/3 and 1/3. And the X's that we pick also have to be in this next set B4. And, and they also have to be in this set that's really tiny, and they have to be in the set like what, like -10 to the like -100, +10 to the -100, 1/1. That's a Google, right? 1 to the
Mm,
100 is a Google.
I think so.
Yeah, it's the largest number that has a name. So the point is, the X's that are in this big intersection, they have to be in all of them, no matter how tiny these sets get.
So would that one be -infinity to infinity? No.
Well, -infinity to infinity would include the number 2, and that's not even in the first set that we're dealing with.
Would it
True.
be B4? Because that's the smallest it can get.
You mean from 4? No,
Yeah.
no, no, this thing gets smaller and smaller. It's this set from -1 to 1 intersected with this set. Listen, what is this set from -1 to 1 intersect from -1/2 to 1/2? Let's just look at that. What
Well,
is B1 intersect B2? We're looking for elements that are in both B1 and in B2. So which real numbers, X, are in this intersection?
B1.
Are you telling me that like the number out
No,
here, 3/4, is in the set from -1/2 to 1/2?
that's
Look,
wrong.
here's the set from this green set is from -1/2 to 1/2, right?
Yes.
Anything outside of that is not in the intersection because the intersection says X is only in B1 intersect B2 if X is in both this set and also X has to be in this set.
-1/2 to 1/2.
Thank you. Only the elements in the smaller set are in. Now that pen is shot, even though it's got ink in it. I hate that. What a waste of money. Yeah. These elements, Rebecca, does that make sense that the elements that are in the green set are in the green set and in the bigger set?
Yeah, because I said before, because it's the smallest because it's in every set.
Okay, great. So you understand. And then if we take B1 intersect B2 intersect B3, everybody, then we're looking for elements in the smallest of these because these are nested. It would be B3, right?
Yes.
And I mean, and if it's the intersection from k equals 1 to 4, then that intersection is B4. And if it was the intersection from k equals 1 to 5, it would be B5, right? And if it's the intersection from k equals 1 to forever, then there's only one number that's guaranteed to be in all of those, no matter how large k gets. Because
0.
yeah, only 0 is going to be in all of them. Because the minute you try to, so like here's 0, right? The minute you try to put an X, let's say there's an X right there, and you say, oh, that X is going to be in this big intersection also, I will say, nope. No matter how tiny your X is, no matter how close you pick X to be to 0, we can find a little square bracket set that's tinier than the space between X and 0, and then that set won't include X as an element. So X cannot be in the intersection of this tiny square bracket set with any of the other ones. See what I mean?
Mm-hmm.
The only X that's guaranteed to always persist in all of them is 0. All right, other questions. Wow, we're already at 7:55. We wanted to look at some set stuff. Rebecca, did you have other questions about set operations before we look at some of these set questions, some of these set proofs?
Yeah, like when they equal one another.
Yeah, let's do that one. All right, so let me just grab special homework 11. And there was a nice proof about set equality in there. I think it was problem number 3. What do you need, Rocky? My gosh, my dog is being a buggeroo. Do you need to go potty? You just want to go out and bark and see if the cat left any food out there. All right. So, number 3, and this is from either special homework number 11 or worksheet, on chapter 6, whatever section you're in. So it said this, it said A minus B quantity union B minus A is equal to A union B quantity minus A intersect B. This is a classic set question. This is called the symmetric difference. If you actually drew a picture of this set, it's a really pretty little set. Here's A and here's B. And so the set is A minus B. So think about everything that's in A, but subtract away the part of A that's also in B. That would be the cat's eye. So this area right over here, this cookie with the bite out of it, is A minus B. Union, so that's or B minus A. This region right here is the region B minus A. So this is A minus B, union B minus A. But you can get that also by taking the union, which would be everything filled in that's in A or in B. So you would shade all three of these regions, but then subtract away the elements that are in A intersect B, but that's just the cat's eye. So if you took away the cat's eye from the shaded union, then you would get exactly this again. They're the same set. So how do we prove it? Prove. All right, so in the proof, of course, we give ourselves let A be sets in the universe U, even though there's not a set complement operator in play here, we can still just imagine we've got a universe. So we're going to prove subset inclusion in two directions because the strategy for proving set equality is to prove subset inclusion in the one direction, and then we turn around and we prove subset inclusion in the other direction. What's up, Brock? My dog is really you're a good boy. Is there we got some riffraff in the house? You're a good boy. He never barks. He only barks when there's somebody on the property. We're not opening the door, Rock. No, we're not opening the door. I live in sort of a shady neighborhood. You're a good boy. Yes, good boy. All right. So we want to take an element X that's in this set on the left, right? And then we want to chase it. It's called an element chasing argument. We'll chase X until it's over here. And then that will have proven subset inclusion, in this direction, left to right. Then we're going to turn around and assume X is over here in the second half of our big proof. So our little other proof, it's like too many proofs. Take X from this set over here and we'll chase it until it lives over there. Does that make sense? That's our strategy?
Yeah.
All right, so y'all help me. Let's let X, oh yeah, what are we doing first? We're going to go this way, left to right. Let your reader know. Okay, so let's let X be an element of A minus B union B minus A. Now, if you missed this lecture, here's the inside scoop that's really helpful to know. We break down what it means for X to be in this set in sort of the opposite order that we would build this set. And what am I talking about? Okay, let's just suppose I gave you a set A and it had some elements in it, and I gave you a set B and it had some elements in it, and I asked you to find this set, A minus B union B minus A. Well, what would you do first if you were trying to construct this set? You tell me.
For the first part, wouldn't you take out everything that's in A? Whatever's left in B?
That would be B minus A. So we would find B minus A,
Okay.
and then we would need to find
A
A
minus B.
minus B. Right. Where we start with the elements of A, throw away everything that's in B, subtract away B, and then like you said, Rebecca, to find B minus A, we start with B, and we throw away anything that's in A. We only keep the elements of B that we didn't subtract away, right? So we would find A minus B and B minus A first. So we all understand that if we were constructing this set, we would first find these sets that are inside the parentheses, and then we would take their union at the very end, right? We would union these two up, right? Well, when we're breaking it down, when we're trying to push through a set proof, we start with this last operator. The last kind of the big operator that would happen last, if we were building the set, that's what we break down first, okay? And that's the main thing to understand is we're deconstructing what it means for X to be in this set. So we do that in the order opposite that we would do if we were constructing that set. So let's break down this union first. Okay, so by definition of union, you tell me, by definition of union, we know what? What does this union tell us?
It's either in A or B or in both.
Yeah, I don't know where you're getting all that. It's either in A minus B or X, it is X, right? X is either in A minus B. Let's just keep it simple. We know X is an element of A minus B or X is an element of B minus A. See how I'm just going to just attack it one baby step at a time? Let's just break down this union to an or statement. Are you with me?
Yeah.
We don't want to try to dig too deep at one, all at the same time because we're going to get it wrong. But can you agree for sure that what this union means is it means we have an or statement about X being an element of this component or this other component, whatever they happen to look like. Here they look like A minus B and B minus A.
Yes.
All right, so then stop. What is wrong with you? Rocky, goodness gracious, sit down. Come on. You're a good boy. Come on, sit down. He never acts this way. Maybe he is acting this way because he's trying to get me to give him another meaty bone. Maybe he thinks that if he scares away a non-existent burglar, then he deserves another meaty bone. Yeah, you love those. Lie down. So we have two cases, people, because we have an or statement. An or always leads to cases. Right now, we've got cases right off the bat, right off the get-go, because the first operator we're breaking down is an or operator, okay? A union. Now, let's look at what we wish to show. In both of these cases, we wish to show that X is an element of A union B minus A intersect B. Can we break that down just a little bit more? I.e., what do we really wish to show? Well, it's the same game when we're trying to break down what it means for X to be in this set. We break down the last operator that would get executed if we were actually constructing this set. What is the last operator that would be executed if we were building this set, folks?
The minus?
Yeah. So what does it mean for X to be in A union B minus A intersect B? Can we just break that down, just the set minus part? All right, so let's talk about set difference. X in a set difference means X is in the first set. So X is in A union B, and because we're subtracting away the second set, X is not in the set that's to the right of the operator. Set minus is not a symmetric operator, okay? It's not like union or intersection. This is what it means for X to be in this set difference. It is in the first one, and X is not in the second one. Basically, if we were building the set, we would look at A union B and we would throw away or subtract away any elements that were in A intersect B. And that would leave us with elements that are in this set difference. Does that make sense?
Yeah.
So in both cases, I mean, we're just looking at the wish right here. You know, what does it mean to get X into that set? This is in focus. In both this case one and in this case two, what we really need to show is that X is in A union B and X is not in A intersect B. So let's go ahead and look at case one. Because remember, our cases arose from X being in this union to begin with. So what should we suppose for case one?
X is an element in A minus B.
Good. All right, tell me what that means. And we'll just keep our wish in the back of our mind. We're heading toward this, but let's just break down what does that mean, that X is in A minus B?
That X is an element of A and is not an element of B.
Perfect. Very good. This means X is an element of A and X is not an element of B. Everybody on the same page here? Great. Well, that's going to be enough for us to get X in A union B and to get X not in A intersect B. Let's think about why that's true. If X is in A, and we do have X in A in this case, doesn't that mean that X is in A or X is in B?
Yes.
So, since X is in A, we see that X is in A union B just by definition of union, right? If it's in A, then it's in A or in B, so it's in the union. Do you agree with that, Sydney?
Yes.
Yeah. So we've got the half of what we need to be done, right? We're trying to get this wish in this case one. We're going to get it in case two too, but let's just get it in case one. We got that X is in A union B. Why? Because it was in A, you know. Now we have to get the other thing. Why is X not in A intersect B? Why do we know we can say that?
I'm sorry, can you repeat that?
All right. Do we all agree we know that X is an element of A union B?
Yes.
The other thing we need to show is that X is not in A intersect B, because that's the other half of what we need to be able to show that X is in A union B minus A intersect B. We have to get the minus part. We have to show X is not in A intersect B. Well, let's just look at what we've got right here.
Is it because since we have X is in A and X is not in B, if we subtract A minus B and get rid of the A, I mean, then X wouldn't be there anymore?
Well, we're not going to be able to get rid of the A because in this case, X is in A. We're not going to get rid of that.
Wait, so if X is in A or B and X is not in B, X cannot be in A and B.
Yeah, we know X can't be in both because X isn't in B. I mean, the fact that X was in A minus B by definition of set difference, right? This is by definition of set difference, and I should have said that. We had X is in A and X is not in B. X being in A is enough for us to say X is in A union B, right? Because union means or. But X is not in B because X was in A minus B. We're guaranteed X is not in B. If so, what would it take for X to be in A intersect B? Like, what does that mean that X is in A intersect B? We want that it's not. But what would it mean for X to be in A intersect B?
For X to be in A and in B.
That's right. That's the only way X gets to be in A intersect B is if X is in A, which we do have, but X also has to be in B, and we don't have that. In fact, since X is not in B, we see X is not in A intersect B by definition of intersection. You don't get to be in the intersection if you're not in both of the sets in the intersection, if it's a two-set intersection. Does that make sense?
Yes.
So what do we have? We have that X is in A union B because it was in A. And we have that X is not in A intersect B. So let's hold that thought. That's going to be enough for us to say, hey, that's the definition of X as an element of A union B minus A intersect B, because this is the definition of set difference for these two. See what I mean? Like we're right there, but I don't want to write everything twice. So let's go ahead and see if we can get these two things true in case two. Then we can drop out of the cases and say, hey, in both cases, we got X is in A union B, and we showed X is not in A intersect B. And then we'll just be able to say that means for sure X is in that set. See what the strategy is here?
Yeah.
So what should we suppose for case two? What's our hypothesis for case two, folks?
Suppose X is an element of B minus A.
Nice. And you know why I do things like this? Just so I can easily go back up and see, you know, what my cases are. The minute I see or, I go ahead and write this kind of stuff and it helps me because I might forget what I'm doing by the time I get to here. But then I can just say, oh, okay, I got it. All right, so what does it mean? What does it mean? We've got X is an element of B minus A. Let's break that down.
This means X is an element of B and X is not an element of A.
Perfect. And that's by definition of
Set difference.
nice. Better than what I did the first time. Okay. And now we're keeping our eye on the prize. We see where we're headed. So how are we going to get what we wish from what we have? We have that X is in B and we have X is not in A. So let's just take our reader by the hand so our reader doesn't have to work too hard. Anybody?
Wait, if X is an element of B, wouldn't X be an element of A or B?
Yes. And it's no if about it. It's a fact in this case. Since X is an element of B, that means X is an element of A or X is an element of B, right? Is true, right? So where do we get X? So X is an element of A union B by definition of union. I wrote a little more here, but that's because you said it and you're right. So we've got X is an element of A union B. Now what? Look at what our wish is.
Since X is an element of A union B, mm,
So we got this, right? We got that. But
wait,
we also got to get this part.
yes, but it can be in both.
Well, why not? Look at what we've got. We can't just say that. We got to back it up with the information from this case.
So since X is an element of B and X is not an element of A, X can't be in A and B.
That's right. In fact, we can just say since X is not in A, we can't have X in A and X in B, right? Because I mean, it's true that it's in B, but the fact of the matter is we're trying to figure out why it can't be in both. So X is not an element of A intersect B because it's not in A. That's really, yeah, it's true it's in B, but it's not in A. And that's why it's not in both. It's because it's not in A. And that's by definition of intersection. Sort of like by definition of the negation of intersection, really, technically. But look what we've got now. In both case one and in case two, we got that X is in A union B, and we argued different reasons, right? Sort of like symmetric opposite reasons, but X is not in A intersect B in both cases. Well, now we can say, hey, in both cases, we found X is an element of A union B, and X is not an element of A intersect B. So where is X? Look at our wish. See, having the wish here helps guide you. Like, what were we trying to get?
So X exists in A union B minus A intersect B.
Nice. By definition of
Set difference.
perfect. See how we got it? And we got it like we didn't cheat or pull the wool over. We really broke it down because of this union. We got these two cases, and in each case, we really broke down what we had in our hand, and then we built it back up to what we needed using a good argument. So we can say A minus B union B minus A is a subset of A union B minus A intersect B by definition of subset. Because we started with an element in this set and we showed that that implied that X was in this other set. So we got subset inclusion in this direction. Shall we go the other way and finish this proof?
Yeah.
You sound so excited. I get it. All right, that's three. All right, so now we're going to go back the other way. All right, let me at least. All right, so, and I will post these notes right after our session. So we start with an X in this set, and we're going to break down what it means to be in this set, and then we'll build back up to show that X lives in this set. So we're going to assume X is an element of A union B minus A intersect B. What do we wish to show, folks?
That,
A
yeah, A minus B union B minus A.
I need a complete thought. I need an X.
Oh, X is an element of A minus B union B minus A.
Nice. Yeah, it's an easy mistake to make, but we need to why don't we go ahead and just break this down a little bit, and then at least we'll know what we're really shooting for, i.e., what do we really wish to show? Break down the last operator that gets executed.
X exists in A minus B or X exists in B minus A.
Nice. So if we can show this or that, we are going to be able to just say, hey, that puts X in the union. If we get X in A minus B, we're good because it'll be in the union. Or if we get X in B minus A, we're good because it'll still be in the union. And there'll be two cases, and in one case we'll get this, and in the other case we'll get that. All right, so now let's go ahead and break down our hypothesis, okay? By our hypothesis, what operator do we break down first? Because X is in this set right here.
The minus?
Yeah, I'll just rewrite it. X element of A union B minus A intersect B means, you tell me, what does that mean?
That X is an element of A union B and not an element of A intersect B.
Okay, so X is an element of A union B. X is not an element of A intersect B. All right. So there are numerous ways to correctly write this. But let's just think about what this means. Oh, this is by definition of set difference. I better write that. By definition of set difference. So X being in the union, what does that mean? Tell me in your own words.
That X is an element of A or B or both.
Good. Perfect. Tell me in your own words what it means, because this is an and, so both of these statements are true. Tell me in your own words what it means that X is not in A intersect B.
That X isn't an element of A and B.
Yeah, it's not an element of both.
Would it be a or instead?
Um, no, it's not an element of both. It's not an element of A or it's not an element of B. You're right. It is actually an or statement. Yeah, not an element of A and B means not an element of A or not an element of B or both. But we know it's in one or the other from here. So we know that X is in A or B, but we know it's not in both. See how that is? So
Yeah.
there's, right. So to be really good, I'm just going to, it's not the only way to do it, but the point is, uh, I want to write it in a natural way, but I also want to be methodical enough that it's absolutely airtight. Since X is an element of A union B, let's just break that down. What do we know? We know X is an element of A or X is an element of B. We can all agree on that, right? Like nobody can argue with that. That's what it means. The or both we can say, but we don't need to because if it's in both, then the proof of case one and the proof of case two proves what we want to prove twice for that particular X. If there's an X that's in both. There actually is not an X that's in both, though. Okay? But the point is, in one case, X is in A, but X is still not in A intersect B. And in the other case, X is in B, but it's still not in A intersect B. I mean, that's true no matter which case we're in. So case one, say X is in A. But we know X is not in A intersect B, right? By hypothesis, by our hypothesis. So what do we know? Look at what we're shooting for. We want to get X in A minus B, or we want to get X in B minus A. Well, in this case, X is in A, but it's not in A intersect B. So what do we know about X? It is in A, but it's not in A and B. So where is it not?
A minus B.
It will be in A minus B
I mean,
because,
A A intersect B.
yeah, since it's not in A intersect B, but it is in the A part, what is the only thing that could be making it fail to be in A intersect B if we know
B
it's in A? Yeah, B. So X is
is
not an element of B because X is in A, but not in both A and B. That means the only way that X could fail to be in A intersect B. It's already in A. What else could go bad? Oh, the only thing left would be that it can't be in B. So we know X is not in B. We've got X is in A, right? In this case, because it's in the union. So this is the first case. It is in A, but we know it can't be in B because it's not in A intersect B, right? So where is X if it's in A and not in B? Keep your eye on what you wish. Like keep looking at what you wish because you're kind of trying to head toward that no matter what.
X is in A minus B.
Yeah. So X is an element of A minus B by definition of what?
Set difference.
Yep. So look where we got X. We got X in A minus B in this case. See? And in the other case, we're going to get X in B minus A. And once we get that X is in A minus B or X is in B minus A, then we'll be able to say, oh, well, that puts X in the union. So let's go ahead and write up case 2 now. What's the hypothesis of case 2? Remember where the cases came from? X was in A union B. X was in A or in B. So
A
what?
section B.
Yeah. Well, oh,
Oh, X. Oh, X intersect B. Or X is an element of B.
right. Suppose X is in B, because that's the other case, right? One case was that it's in A. We did that case. But now it's in B. But remember, it's still, look what we're shooting for, right? But X is not in A intersect B, so it must be that what?
X is not in A.
Yeah, and X can't be in A. So it is definitely in B, but we know it's not in both, so it's got to be that it's not in A. So now where is X?
B minus A.
Yep. So X is an element of B minus A by definition of set difference. So we've got, in one case, X is in A minus B. In the other case, X is in B minus A. Well, it's nice job that we kind of sorted our wish out because we've got exactly what we need outside of the cases. So by our cases, we have X is an element of A minus B or X is an element of B minus A in both cases. Where does that put X?
in A minus B union B minus A.
Yeah. Thus, X is an element of A minus B union B minus A by definition of what?
Union.
Nice. What is the matter, Rob? Dog, there's something wrong with my dog. Maybe he needs to go out. Okay, so X being an element of A union B, and we didn't do this at the end of the first half. We should have. But anyway, X in that set, A union B minus A intersect B, does imply X is an element of A minus B union B minus A. That's what we just proved, right? We took an X from there and we showed it in there. So we can say A union B, this is what we wanted to be doing anyway, is a minus B, A intersect B is a subset of A minus B union B minus A by definition of what?
Subset.
Yeah. All right, hang on. I'm going to pause this while I let him out. So do you find that it's better to have Zoom office hours because then you can go back and look at the recording? Or do you want to come in person tomorrow for live office hours?
Either or is fine. I did look at the last recording and I'm probably gonna look at this one too.
So I
Um,
tell you what, so how about we have a pop-up office hour tomorrow from like 8 p.m. to 9 p.m. I'll be home by then.
okay.
Would you rather do that?
Yeah, so I can look at it later. Yeah.
All right, I'll send around an announcement in the morning and then you can have a pop-up and that way if people come to the pop-up office hour, then maybe I can get some stuff done tomorrow between 3:30 and 5. You know, get some stuff, some other stuff done. And then we can have an office hour that is recorded. All right, I'm going to call it a night.
Thank you,
Let's,
Professor.
all right, keep on coming, keep coming back. All right, I'll see you soon.
You have a great rest of your night.
Thank you, you too.
Thank you, Professor. Good night.
Rebecca, thank you so much for coming in. Did you get your questions answered?
Yeah, and I'll probably come back. I don't know about tomorrow because I have to study for another exam.
We're going to try to have them every night.
Okay.
All right,
Thank you.
you're welcome. Bye.